Hey yo, today we're looking at different types of attributes and how to represent each of them in an ERD. Alright, let's get started. Suppose we are designing a database for UNSW. Then what are the things that we want to store information about? Well, the obvious answer would be something like students, courses, lecturers, and so on. But for the purposes of this video, let's focus on just the students. Now, for a given student, what kinds of information about the student do we want to record in the database? I'll say their name, maybe their gender, how old they are, where they live, and their phone number, or their phone numbers if they're using more than one. So student is the entity set we want to model in our ERD, and the rest of these are simply the attributes that are associated with the entity set students. In ER modeling, attributes are denoted with an oval and a line connecting it to the entity set. This is like the default style that applies to simple attributes like name, gender, and address, which are the things that you can represent as a single string. For example, if Sam Smith is a student's full name, then you can store the whole thing as a single piece of data. But one of the common things that the uni does with students' names is to make a list of students sorted by their family names, which you might be familiar with from some classes taking student roles. But if you instead try to order students by their full names, you're not going to get the result you want. So what we normally do is store the given name and the family name as separate pieces of data, or two separate strings. This way, for any group of students in the database, you can easily grab their last names and use them directly for sorting the students in order. To convey this idea on the diagram, all you have to do is branch out from the main attribute, with one branch for given name and the other for family name. So that's an example of a composite attribute consisting of two component attributes. And you can do the same with address. Perhaps we can separate it out into three parts: street, town, and postcode. If you want, you can break it down even further by, for example, dividing the street into its number component and the name component. But since I don't really see much use of these fine-grained components by themselves, I'm just going to undo what I did and move on to the next attribute, which is going to be student's age. You can't really divide age into smaller parts, so it's gotta be a simple attribute like gender, meaning we store it as a single integer. But this has a bit of a problem. Student's age is going to be changing every year, so every year when a student becomes a year older, you'd have to manually go and update their age on the database. Plus, it's not just a single student we're talking about. It's about 50,000 students coming to uni, or maybe even more than that. So usually what we do is instead store values that do not change as frequently. In this case, we can store the student's date of birth, aka DOB. This way, you never have to update the database every time a student gets a year older, because the only thing we are storing is their birthday, and that should never change. And if you do want to know about their current age instead of when they were born, you can simply ask the database system to figure it out for you from the today's date and the student's date of birth. To show that we are actually interested in knowing students' age, what you want to do is keep it as an attribute of student. But since it's not going to be a stored attribute, we are going to turn it into what's called a derived attribute. Derived meaning it's not actually stored on the database, but instead it's calculated from some sort of data that exists on the database. Now have a look at all the attributes that we've seen so far. Every student has exactly one name and exactly one birthday, and it's the same for the rest of the attributes. But for this attribute, some students might have more than one phone numbers. Perhaps a student has one for her mobile and a different one that she uses at home or at work. In other words, this attribute has to be able to hold not just a single value, but multiple values. Hence we call it a multi-valued attribute. And we denote it using a double oval. Multi-oval for multi-valued attributes and single oval for single-valued attributes. To sum things up, here we have grouped the terms into pairs that mean the opposite of each other. So every attribute has to be either simple or composite, single-valued or multi-valued, stored or derived. For example, gender is simple, single-valued and stored. Age is simple, single-valued but derived. Name is composite, single-valued and stored. And finally, contact numbers is simple, multi-valued and stored. One more thing that you might want to take away is if an attribute is both simple and single-valued, we call it atomic. Atomic meaning we can't break it down into smaller parts. So that basically illustrates all the different types of attributes you can find in ER modeling. Alright, now have a look at this. Here we have some examples of student records which follow the template defined by our student data model. The first student we have is Sam Smith. Born in year 2000, lives on 7 Rainbow Road in Kensington, and he's got 2 contact numbers. Then we got Mary Williams and a different Sam Smith, each with their own set of values for the attributes. Each of these students is what we refer to as an entity or an entity instance. It's an individual object that we store information about. On the other hand, what we've represented over here in our ERD is called an entity set, which is like the category that all of these entities fall under. So that was just a quick note on the difference between entities and entity sets. Okay, now suppose that in a different part of the database, there's a record saying Sam Smith has received a HD in COM1531. So we go back to our list of students and look for Sam Smith. But turns out we got 2 Sam Smiths in the database, and there's simply no way for us to tell which one of these 2 Sams that the record is referring to. To avoid this kind of ambiguity, what we really need is some sort of an attribute whose value is going to be different for every student. This way the database and yourself can always rely on that attribute to tell every student apart from all the others. In other words, we need an attribute that can uniquely identify each entity. And this special attribute is what we refer to as a key. Well, if you think about it, no one at UNSW has the same ZID as another person. As a matter of fact, it's an artificial key made by UNSW, so it's designed to be unique to every student. So all you have to do to fix this diagram is simply add ZID as an additional attribute, and underline its name to indicate that it's the key attribute of student. And that's it, now we have our very first ERD of the series. Thanks for watching, I will see you in the next video.